Okay, so this last module is going to be on magnetostatics. Okay, and the goal of today is to actually get over this first bullet point here: magnetic forces and torques. So I want to bring this chapter about from sort of a practical standpoint. You know, there's kind of two things that you were interested in doing. I'd say magnetostatics allows you to create magnetic forces. If you run a current through a wire, you can create, if there is, a magnetic field can create a force on moving charges. Okay, so this is a magnetic field acting on moving charges. And it can also go the other way around. Moving charges can also create a magnetic field. Okay, when a magnetic field acts on moving charges, it creates a force, and that force is called the Lorentz force. It can cause a wire to move. It can cause a loop of wire to rotate. All right, and the reason this is interesting from a practical standpoint is it's the basis for motors. And as we'll see later, it's actually the basis for electric generators as well. And the next one, the Biot-Savart law, that describes how a current can generate a magnetic field. Okay, does anyone know what the uses for that is? If a current can generate a magnetic field. Oh yeah, that's a great one. Maglev. Magnetic levitation trains rely on that. Also, yeah, just generally electromagnets. Electromagnetics are used in cars. I know a lot of you work in the car industry. Does anyone know where electromagnetics are used in vehicles?
Braking.
Yeah. Those are two. So one is the electromagnetics are used in door locks. Right. There's an electromagnetic that moves the door lock from one position to the other. Regenerative braking, I think Noah was saying that. So that involves electromagnetics as well. Not directly an electromagnet, but it has concepts of a magnet.
A magnet, like when you brake, like it's the change in the force between the magnets, like affects the charge that gets back to the battery or something kind of similar to that.
Yeah, in regenerative braking, it's where the rotation of the rotation of the wheel is feeding back and actually generating current. So it's acting as a turbine. And there's some magnetic braking that happens at the same time. We have several graduate courses in that kind of stuff if you're interested. We're just going to be going over the very basics here in this class. So those are the two we're going to get to today, and we'll see how much of it, the remainder of the chapter we get to. We'll probably end up talking about Maxwell's equations for magnetostatics. We'll probably end up talking about magnetic properties of material, and if we have a chance, we'll probably get into inductance, maybe. Magnetic energy, I'm not sure if we'll get a chance to go over this time around. Okay. So let's go back to Maxwell's equations. All right, this is a good place to start. You've seen this slide before, right? We talked about the first thing that we talked about in this class were the four Maxwell's equations. The first two had to do with electric fields. So del dot V is equal to rho V. If you remember that, if we describe that in English, what that means is that the electric field lines diverge from any point charges. That's Maxwell equation number one. Rho V represents a charge at a point in space, and del dot D, the divergence of D. That means this statement basically says that the electric field diverges, and the amount of divergence that you have depends on how much charge you have. Electric field lines point away from positive charge and towards negative charge. The second Maxwell equation, del dot E is equal to negative dB dt. Now remember in statics, in statics these two relationships go to zero. Wherever you have a d dt, that term goes to zero when you're talking about statics. So in electrostatics, del cross E is equal to zero. Basically the curl of the electric field is equal to zero. All right, we're going to find that that's quite different in magnetostatics. In a way, it's kind of the inverse of electrostatics. The first Maxwell equation in magnetostatics is del dot B is equal to 0. All right. In electrostatics, you found that field lines point away from charges. All right, so you can have a situation like this where I'm going to jump ahead here. In electrostatics, you can have a situation like this where the field lines are diverging away from a point in space. Del dot V is equal to rho V. Now, in magnetic fields, you'll never have a situation where magnetic field lines are pointing away from a single magnetic element. The magnetic fields always form little circles. Okay, that's one piece of intuition. We'll come back to this in a second, but I just want to point out the differences between electrostatics and magnetostatics. All right, you can have a divergence of an electric field, but you can't have divergence of a magnetic field. Del dot B is equal to 0. And this one, the last one, del cross H is equal to J plus D dt. Now, in statics, we ignore this last term, and we're left with del cross H is equal to J. What does that tell us? What's your intuition based on your knowledge of curl? Del cross H. Remember, H is related to the magnetic field. B and H are related. B and H are related just like D and E are related. Okay, B is equal to mu times H. So coming back to this, what does it mean? Del cross H equals J.
The current is going to create a magnetic field that rotates around it.
Exactly. Exactly.
Or the other way around. If you have a current, you can generate a magnetic field going perpendicular to the plane of rotation.
Correct. Correct. So there's a relationship between a magnetic field and current, where if you have a current J, then that's going to create a del cross H. Del cross H means a rotation of the magnetic field. So the way we can think about that is if you have current going through a wire, the magnetic field curls around the wire. It actually looks something like this. I'm getting ahead of myself, but we'll come back to this in a second. It looks something like this. Current going through a wire, magnetic field lines wrap around it like that. Okay, so those are the equations for magnetostatics. No divergence, but you can have a curl. And the difference is the opposite of electrostatics, where in electrostatics you can have divergence, but you don't have curl of electric fields. Any questions so far? The other important part about statics is that magnetic and electric fields are decoupled from one another. These two equations here just involve electric fields. These two equations here just involve magnetic fields. If you have time-varying fields, then you have dB dt in this second Maxwell equation and dd dt in the fourth Maxwell equation. These two terms end up coupling electrical and magnetic fields together. All right? So in time-varying fields, you'll end up using the full form of the Maxwell's equations. And in statics, you just use these decoupled versions. All right, so let's define what those equations are. So we talked about Gauss's law and Faraday's law of induction when we talked about electrostatics. Now let's talk about the third and fourth one. Number 3 is Gauss's law for magnetism. It's a fundamental rule of magnetic fields. There are no magnetic point sources. In electric fields, you can have point sources. A point source would be just a positive charge in space or a negative charge in space. You can't have those in magnetic fields. I'll show you a diagram of that. The fourth one is Ampere's circuit law. This is saying that magnetic fields can be generated in two ways, by electrical current and by time-varying electric fields. Electrical current is J, time varying electric fields is d dt. All right, but since we're working with statics, we're going to ignore the second thing here. So defining the terms, the magnetic field variables, B is equal to mu H. So B is the magnetic flux density, also called the magnetic field or the magnetic induction. H is called the magnetic field intensity. And it's also called the magnetic field strength. And they're related together by this term mu. Just like D is equal to epsilon E, in magnetics you have B is equal to mu H. So mu is something called magnetic permeability, which is the ability of a material to allow a magnetic field within itself. So remember back to the last module when we talked about the dielectric constant, epsilon. What was epsilon?
The permittivity?
It is called the permittivity. And what was the definition? What did it mean? What was the physical meaning of the dielectric constant?
So how much tells us about the material, how conductive it is?
Not how conductive it is. How conductive it is the other one. It's the conductivity, sigma.
Okay.
But the dielectric constant or the permittivity is epsilon. What does epsilon tell us?
It's the ease with which electric field goes through it. That's
Well, not quite the ease with which electric fields go through. It relates to how polarizable the material is.
okay.
How strong an electric field develops within the material. Okay. So if you have, when we talked about electric fields, the more polar the molecule is, the higher the dielectric constant. Because when those dipoles line up with the electric field, they actually create a small electric field within themselves. So this has an amplification effect. So similarly, in short, the dielectric constant tells you if you have a high dielectric constant, that means it can sustain higher electric fields, or it generates higher electric fields within the material when these dipoles align. Similarly, with magnetic fields, the higher the magnetic permeability, the larger the magnetic field strength you can sustain, or the larger magnetic field you can have inside the material. Okay, when we talk about magnetics, what we'll find is that the magnetic field, if you have a magnetic field in space, that magnetic field can become concentrated in areas where there's high magnetic permeability. So high permeability materials can act as flux concentrators, if you will. All right, for now, just assume it's just a constant. It depends on the properties of the material. We'll come back to that later and look more at what determines the magnetic permeability of a material. All right, so these two relationships, we have two relations. One specifies the divergence of the magnetic field, and another specifies the curl. This says electric here, just ignore that. It says magnetic. So from our understanding of divergence and curl, what do these relationships mean? Magnetic fields, okay, we just went over this. The magnetic fields are divergence-less. There's no such thing as magnetic flow sources, and flux lines always close upon themselves. So in other words, magnetic field lines form loops. Magnetic field lines flow from north to south. And there's no magnetic flow sources. Point sources, just like there are positive and negative charges. I'll get to that in a second. Ampere's law, the right equation, says a circulating magnetic field must be accompanied by a flowing current. So it can go both ways. If you have a circulating magnetic field, something that goes that curls around, it can generate a current. And the opposite is also true. If you have a current that generates a circulating magnetic field. Okay, have you seen anything like this before? In these flux lines? Okay, so what do you notice about this? The flux lines always point from north to south. have you done experiments like this in physics where you you take iron, like metal shavings, and then you put it around a magnet, and you see those shavings form the lines?
Yeah, a long time ago.
Long time ago. Okay, let me just jog everyone's memory here. I'll just pull up a picture on it. You can look online here. All right. Iron filings. There you go. Yeah, I think this is a good good demonstration. All right, you take some iron filings, you put a magnet in there. Those iron filings actually form these patterns, and those patterns are ultimately like how these magnetic field lines, or the structure of the field lines, were discovered. So examples of what field lines might look like: they always go from north to south. Notice they form loops. They go from north, and then they go to south. Here they also flow from north to south like this. They form a flow path, okay, from one to another. So what would happen if you were to say, well, what if you just had a north pole and you didn't have a south pole? Like, what if you took this magnet and you decided, I just want the north pole, and you cut the magnet in half? What's going to happen?
It's gonna create another South Pole.
Yeah.
Yes, exactly. This is an important point. I know that you all have learned this in physics before, but in the context of electromagnetics, is important. Let's say you have a bar magnet like this, the one that we just drew. North south. You say, you know what? I want to get just a north pole, and you decide to cut this in half. After cutting it in half, you'll end up with something like this: north, south, another one. Each piece will end up having its own north and south poles. So the field lines for this look like this. You'll end up with field lines that look like this.
What would happen if it was a spherical?
I'm sorry?
If it was like a ball magnet?
If it was a ball magnet?
Yeah.
A spherical magnet?
Yeah.
You'd still end up with the north and south pole, like if you cut that sphere in half.
No, I mean, what if you had it like normally? How do you determine which side is the north, which side is the south? The ball magnet.
Which side is north and which side is south is determined by
It's like all.
which way the magnetic moments are aligned in the material itself. You can actually use magnets to align those magnetic poles inside the material.
That's why they say don't like force two magnets together. Like, you mess it up.
Well, I mean, if permanent magnets, they have, they've already have their alignment, so it's difficult to change the orientation of a strong permanent magnet. But the strong permanent magnets can be used to pole or align the magnetic dipoles of a less magnetic material. Yeah. So if we compare electrostatic and magnetic fields, again, you'll notice that it's impossible to have a single type of magnetic source. And because of that, you always end up having these lines flowing from north to south. If you compare that with electric fields, in electrostatics, you can have just a positive point charge in space. We actually derived the equations for that without any negative charges. All right, if you just have a point charge in space, the electric field lines point away from it. All right, and the first Maxwell equation describes it. In the case of magnetic fields, you can't just have a north pole. The north pole and south pole are always accompany each other. And as a result of that, you always have field lines that are circulating like this. They have a rotational element to it. All right. So as a result, the divergence of the magnetic field actually is always zero, but you can have a curl component to it. So that's the fundamental difference between electric and magnetic fields. Do you have a question? I see. Oh. All right. More comparisons, because it's always good to, when you're looking at a new topic, it's good if you can put it in the context of a topic that you already know. And I would hope that by now most of you have a pretty good understanding of electrostatics. So in electrostatics, when we're talking about sources, what generates an electric field? Well, you basically have charges, all right, and those charges are designated rho sub v. In magnetostatics, how do you generate a magnetic field? You have a current, all right, and that current can be described by current density J. Fields and fluxes. So in electrostatics, we're dealing with E and D. And magnetostatics, we're dealing with H and B. The material parameters for electrostatics, we talked about epsilon. Epsilon's the dielectric constant. Sigma is the conductivity. And then in magnetostatics, we talk about magnetic permeability instead. Materials like iron the ferromagnetic materials have a high magnetic permeability. And most others materials have magnetic permeabilities just equal to mu naught. Just like we have epsilon naught and epsilon r, we have mu naught and mu r. We'll get more into that later. So the governing equations, we talked about this already. Del dot D is equal to rho v, del cross E is equal to 0. And these are the ones for magnetostatics. The integral forms, remember, this is a good review of the electrostatics chapter. We use both of these forms, okay? Del dot D is equal to rho v. If you remember, we also did this integral form, all right? This was, we called this Gauss's law, right? We defined a Gaussian surface, and we said the surface integral of d dot ds around that Gaussian surface is equal to q, the total charge enclosed within the surface. All right, so this was Gauss's law, and we didn't do this as much, but this is basically the integral form of the second Maxwell equation. Del cross E is equal to 0. If you apply Stokes' theorem, then you get this form. Okay, does anyone remember what Stokes' theorem is and what the divergence theorem is?
Yeah, the divergence is for the surface charge. Right?
Surface charges?
Yes. And then the other one, Stokes for the line integrals.
Stokes was for line integrals, correct. And the divergence theorem was for surfaces, closed surfaces. It says the total flux exiting a surface is equal to the surface integral of the surface integral of the flux. All right, and that was also equal to the volume integral of the divergence, del dot D. All right, I'm not going to go back into the Stokes and divergence theorem. I just wanted to mention how you get from here to here is by the divergence theorem. And then how you get from here to here, the del dot E is equal to 0 to E dot dl is equal to 0, you apply the Stokes theorem. And so we could do the same thing in magnetostatics. If del dot B is equal to 0, we can apply the divergence theorem and get this form. The integral of a closed surface of B dot ds is always equal to 0. The second rule, if you have del cross H is equal to J, you can put this in the integral form as well, applying the Stokes theorem, and you get H dot dl is equal to I. What you're doing is you're taking the double integral of both sides of the equation, double integral of this side, double integral of this side. When you take the double integral of J, you get I. You take the double integral of del cross H, that by the Stokes theorem is equal to the line integral around a contour. Any questions so far? So we're going to be using both forms of the equations, the differential form as well as the integral form. All right. Now, we talked about scalar potential. What was scalar potential in electrostatics?
Voltage. I mean,
What was the meaning of scalar potential, I should say?
well, it's sort of the energy available from a distance across an electric field.
Yeah,
I mean,
energy available. That's a good way of putting it.
Or
Yeah.
can we say how hard we're pushing the electron?
Well, that's the force. That's the force. I think the scalar potential is like a potential energy, right?
Pressure, more like pressure on the electron.
Again, that's referring more to the force. I mean, the potential. I mean, I suppose they're all related, right? When we were talking about potential energy, right? If you put a charge in an electric field and you let that charge go, that electrostatic potential energy is going to be converted to kinetic energy, right? That field will accelerate that charge, and that as it accelerates, the electrostatic potential energy is converted to kinetic energy, right? So electrostatic potential energies, wherever you have a voltage, wherever you have an electric field, that represents the potential to it represents a storage of potential energy, right? So E is equal to negative del V. All right, this related electric field to the scalar potential. All right, wherever you have electric fields, you have some associated electrostatic potential energy. Similarly, with magnetic fields, there's a magnetic potential energy as well. Wherever you have a magnetic field, B, there's something called a scalar magnetic potential, A, and the relationship with B and A is through this relationship. B is equal to del cross A. All right, so it's a little bit different than the definition for electrostatic potential, because this is just the gradient, and this one involves the curl. Energy density equations are actually pretty similar. The energy stored in an electric field is equal to 1/2 times epsilon times E squared. Right? So in a capacitor, you have an electric field. That's an example of energy storage. Similarly, with magnetic fields, you can also have energy storage. If you have an existing magnetic field that has an energy density associated with it, and the equation here is very similar, 1/2 mu times h squared. Forces. Okay, the force on a charge is equal to Q times E. This is the electrical force. And in this module, we're going to learn that there's a magnetic force. And that magnetic force is equal to Q times U cross B. All right, this is what we're going to be spending time talking about next. In terms of circuit elements, you know, what do these rules ultimately translate to when we're doing circuit design? With electrostatics, we talk about capacitors and we talk about resistors. So we did calculations on both in the last exam. In magnetostatics, we talk about inductors. Energy storage. Remember that capacitors were energy storage elements, and so were inductors. In capacitors, the energy storage is in the electric field, and in inductors, the energy storage is in the magnetic field. All right, so we'll talk about inductors, hopefully. All right, so the first concept in the magnetostatics chapter is something called the Lorentz force. And for those of you who've taken courses in physics, you've probably seen this before. You know, even those of you who've worked with electronics and maybe Hall effect sensors, you've maybe seen this before as well. So magnetic field generates a force on a moving charge. I want to make sure that everyone recognizes this is a moving charge. If the charge is stationary, there's no Lorentz force. The Lorentz force is given by this equation, the Fm. So that M stands for magnetic, is equal to Q times U cross B. So U is a velocity and B is the magnetic field. All right, this is the cross product here. Notice that U is a vector and B is a vector. So Lorentz force is a pretty interesting force. You remember with electrostatic fields, the electrostatic force was very simple, right? You create an electric field by, let's say, applying a voltage between two plates. So you have an electric field that looks like this, and we can call that E. And if you put a charge Q on here, then the force on that charge, we call this F, that force is equal to E times Q. All right, this was the Fick rule. So it's just proportional to the electric field and the amount of charge you have. The Lorentz force only applies to moving charge. So let's go back to this diagram here. No. Okay. So the way that we calculate the force, or the way that we represent the force, is we use the right-hand rule to get the orientation proper. So imagine that we have a charge Q, and that Q is that red circle here. All right, and there's a positive charge there. It's moving at a velocity u. Okay, that's denoted by this vector u. So your first finger, your index finger, if everyone wants to sort of try this out, your first finger points in the direction of the charge is moving. So the velocity is going up like this. Your middle finger is pointing in the direction. I'm sorry. Yeah, your middle finger is pointing in the direction of the magnetic field. And your thumb is pointing in the direction of the resulting force. All right, so imagine in this case, your U is going up, B is going into the page. Just a bit on notation here. Wherever you see a cross like this, that means the field is going into the page. If you see a circle with a dot on it, that means it's pointed out of the page, so it's coming towards you. All right, so your first finger is pointing up, your B is pointing, your middle finger is pointing into the page, and your thumb points in the direction of the force that's exerted on the particle. All right, so the right-hand rule in this case, it's index finger, middle finger, and thumb. We've talked about other forms of the right-hand rule where you just have a thumb and you have your fingers curling around like this. So for this one, I personally think it's easier to think about it this way: two fingers and a thumb. All right, so can someone tell me, if the magnetic fields are oriented like this, which way is that particle going to deflect? What is the trajectory going to look like? It's going to curve off to the left. Exactly. So this particle, instead of going in a straight line like this, it will actually end up deflecting off to the left like this. And it's deflected by the magnetic field, magnetic force. So the way we calculate the Lorentz force is just through this simple cross product here. Q is the amount of charge. U is the velocity vector, so it has a magnitude and direction. Cross it with B, the magnetic field. All right. So the example that I gave here is when U, B are orthogonal to each other. They're not always going to be orthogonal to each other, right? These fields can be pointed in any arbitrary direction that you want. So that's when you would want to use the cross product. Okay, and remember the cross product is equal to So let's just put an equation here. So we just put follow the Q here. And the cross product U cross B is equal to the magnitude of U, the magnitude of B, times, does anyone remember what that last term is? It's sine theta. And theta is the angle between U and B. All right, and with the cross product, there's also a vector associated with it. So that's the n hat vector. N hat is the vector that's perpendicular to both U and B. This diagram here shows what happens when you have a negative charge. Okay, at the bottom you see the diagram of the positive charge. That's the example that we just did. If if everyone wants to remind ourselves here, like U is pointing to the right, so that's your first finger. Your middle finger is pointing in the direction of the magnetic field. I'm not flicking anyone off here. It's just that's the direction of the magnetic field. And the force, my thumb points in the direction of the force. So you can see that the particle will deflect off to the right here like this. But if you have a negative charge, so this example here, a negative charge, then the force will be in the opposite direction. Okay? So this is the force with the positive charge, and you have to negate the force. You have to go in the opposite direction if you have a negative charge. All right? Now, some people like to do this. This may be helpful for you. It may not be helpful for you, but some people like to use the left-hand rule for negative charges. So again, if you want to try it, you can try it. Your first finger points in the direction that the electron is moving, the negative charge is moving. Your middle finger points in the direction of the magnetic field, and your thumb points in the direction of the force. All right? I prefer to just use the right-hand rule and then just take the force in the opposite direction. Questions? All right. I was supposed to cover this up, but okay, so there you have it. This is an example of the Lorentz force. An electron is moving at a speed of 10 to the 6th meters per second in the y direction. The magnetic field strength is 1 Tesla and it's oriented in the z direction. What is the magnitude and direction of the Lorentz force on the particle? All right, so I want everyone to just use the right-hand rule to get your direction straight. All right, this is x, this is y, and this is z, your standard Cartesian system. All right, this is saying that the electron is moving at a speed of 10 to the 6 meters per second in the y direction. So u is pointing this way. All right. The magnetic field is pointed in the z direction. So this is the direction of B. And so it's asking you what is the magnitude and direction of the Lorentz force on the particle. All right, so the first thing you need to know is, okay, we're dealing with an electron here. All right, so the electron is moving this way. All right, so we have to use the right-hand rule and negate it, or we just use the left-hand rule. All right, so your first finger points in the direction that the electron is moving, is pointed in the y direction. Your middle finger is pointing in the b direction. So your thumb is pointing in the positive x direction, right? The thumb is pointing in the positive x hat direction, but you have to negate that, so you have to take it in the negative x hat direction. So the resulting force here is going to be negative x hat is going to be the direction of it. Okay.
So isn't it going to be coming out of the? So the thumb is for the force, right?
No. First finger is the direction. Middle finger is the magnetic field. The thumb is the force. Oh, is that what you said? Did you say the thumb
I
is
said the thumb is the force.
the thumb is the force? Yeah, you're right. I'm sorry. Listen.
Okay, if the thumb was the force, then it's supposed to be coming out of the paper, right?
No.
Well, let's look at this example, right? If your first finger is pointing in the y-hat direction, right? I should, since everyone's screen is this way, right? First finger is pointing in this direction.
Okay.
Middle finger is pointing up in the direction of the magnetic field. Your thumb is pointing in the x-hat direction, right?
So that's what I'm saying, out of the page.
Yes. So if it was a positive moving charge, then the force would be in the direction of the thumb. But since it's a negative charge, since it's an electron, we have to negate that.
Inside it, okay.
Yeah. You got it. Okay. So when we have the directions, that's the other part is fairly straightforward here because everything is 90 degrees with each other. Right? Everything is orthogonal. So in this case, we just have to multiply them out. So 1.6 Q is 1.6 times 10 to the negative 19. That's the charge on an electron. So the negative sign comes there. 10 to the 6th is the velocity. And this should be cross. This should not be a plus sign. This should be a cross sign. Crossed with 1 times z hat, because the units for magnetic field is Tesla. So it's just 1 Tesla times z hat. All right, a Tesla is actually a pretty large magnetic field. You know, has anyone ever been in an MRI before?
I have.
You have?
Twice.
You have. So like the magnetic fields in the MRIs can be a Tesla or more.
Yeah, it's so loud.
What's that?
It's so loud.
Yes, they are loud.
Yeah, why is it that loud?
I am not the best person to answer that question. I'm not sure where all the noise comes from. I know that it is a very, very powerful magnet.
Yeah.
You need that for imaging purposes. I'll have to ask my wife. She's a medical physicist. So. Okay. So this is a very simple question. So it can be easily done. There's no sign term that you have to consider here. But let me just show you that this, if we want to do this calculation the best way, if we're doing Q equals Q times mu cross B, it's better to do it this way. Say Q magnitude of U magnitude of B times sine of theta U B. So the angle between the two. And then the n hat vector. Okay? So this is the general equation. I would use this approach if the fields are not orthogonal with one another. This is the most general equation, and it will work. Every time. All right. So the Q in this case is negative 1.6 times 10 to the negative 19. So that's the Q. The magnitude of U is 10 to the 6th. That's the magnitude of the velocity. The magnitude of the magnetic field is 1. All right, sine. And what's the angle between the two? In this case, the angle is 90 degrees.
So it's 1.
So sine of 90 comes out to 1, correct? And n hat. N hat is the vector that is perpendicular to U and B. Okay, so that in this case, if we look at U is pointing in this direction, B is pointing in this direction. The vector that is perpendicular to both is the x hat vector. Okay, and this vector here can be found using the right-hand rule. That's what we just did. Okay, always use the right-hand rule when you're finding this n hat. Notice that the negative sign, the fact that we have an electron, comes out here. The fact that the Q is negative. Okay. So if you're trying to find n hat, your first finger points towards U, your middle finger points towards B, and your thumb will point towards the this n hat vector. And in this case, it is x hat. Okay? So this is where the x hat comes from. The negative comes from here. All right? And so this answer comes out to the same. It's negative 1.6 times 10 to the negative 13 x hat. And the units for force is newtons. Pretty simple calculation. Any questions on that?
So this is the same thing, but another rule?
What's that?
This is a different formula?
No, it's actually the same formula.
So U cross B translates into that for U diagonal B.
Yeah, U cross B translates into this. This is the definition of the cross product. From, if you look back at the notes from Module 2.
And that's just a much faster way to do it than having to actually do the full vector determinant, which
Oh, yes.
would be, if you had more complicated vectors, then
Yes.
y and z is what you actually have to do.
Yes. Correct. Yeah, I mean, Isaac brought up a good point. Like, you can also, the way you find the cross product, remember about using the determinants, you can also use that approach too. This is a little bit longer. This is quicker.
Well, yes, I'm assuming that's more practical when you have complicated vectors, though, because
Yeah.
Especially if they're non-uniform vectors, if you actually have vector equations that you're trying to cross,
Mm-hmm.
theta's isn't going to be the
It's
same
not
all the time. So
determinable. Yeah, correct. So yeah, in those general cases, you can also use the definition of the cross product. All right, good. So now we can look at the total electromagnetic force. And the total electromagnetic force is nothing more than just the electric force plus the magnetic force. We just figured out what the magnetic force was. That's the Lorentz force. And just remember from Module 4, we just talked about it, is that the electrical force is equal to E times Q. The Fick rule. So if we add those up, we want to find the total charge, the total force on this moving charged particle. There's some of it is the electrical force, some of it's the magnetic force. You just add the two up. So the electric force is equal to Q times E. The magnetic force is equal to Q times mu cross B. So this is the Lorentz force. And if you just pull out the Q and you put it into a compact form like this, it's the total electromagnetic force is equal to Q, the magnitude of charge, times E, the electric field lines, the electric field vector, plus U cross B. All right, and this U should be a vector. Let me fix that right now before I forget. Just make this bold, so we all know it's a vector quantity. And this one here, this should also be bold. Electric field is vector quantity. All right. I thought you might like to see an application of the Lorentz force and electromagnetic forces, something that we actually use them for. Has anyone heard of mass spectrometry? Anyone heard of the term?
yes,
So have you heard about it in the context of chemistry or physics?
organic chem lab.
Organic chem lab, yes. So what did you use mass spec for in the organic chem lab?
Crap, I don't know what we were looking at anymore. It's been quite a few years now. I just know that we took mixtures and then tried to purify one and then ran through mass spec to determine how well we had done.
Yeah.
If you've got
Absolutely.
spikes over here, mean that you still have too much of this, of whatever the extra component was.
Right. So mass spec generally is used by chemists and material scientists and a lot of biologists also to basically look at you want to know what the sample is. Okay, I'm trying to explain this in very simple terms. if we want to know what's in a material, and material is made up of a bunch of atoms, right? Okay, and what a mass spec does is it takes like a mixture or molecules. It breaks up all those molecules into individual chunks. Okay, and each one of those chunks could be an atom. It could be like a small group of atoms, but each one of those atoms or small groups of atoms have a charge and mass associated with it. For example, nitrogen. If you had like nitrogen has a certain mass associated with it, right? Hydrogen ion, like H+, it has a charge and has a mass associated with it. Take a mixture and you break it up into these small fragments, and each one of those fragments goes into this mass spectrometer, and due to the Lorentz force, they actually travel different paths, and you can quantify each one of those different components that you have in the mixture. And then you can use a computer program to piece together what all those fragments were. You can figure out what all those fragments were, and then ultimately get a guess at what molecule you started off with. It's a really, really cool concept. A very, very powerful concept. Like, chemists will tell you mass spectrometry is kind of the a gold standard detection technique. So I just want to bring this up because this class can be dry at times, but it's nice if you can see the applications of some of these very fundamental rules. So I'm just going to zoom in on this here. All right, so let's say you have an ion, okay, and let's say it's a positive ion. You have a bunch of positive ions, and they are moving through in this direction, so they're accelerated from here to here using an electric field. All right, so can someone tell me, if these are positive ions, which way is the electric field oriented?
Right.
Why is it left to right? I'm sorry?
Electric field just goes from positive to negative.
Electric field goes from positive to negative. If the particles are being accelerated from left to right, that means the electric field must have been from left to right also. These positive particles move in the same direction as the electric field. All right. So that's the electric force, F equals EQ. The particles get accelerated this way. Now what happens here is that these particles already have a high velocity, right? So they're moving charges. Moving charges means you can have Lorentz force. The charge is not moving, you can't have Lorentz force. Remember that. So you throw in a magnet here, and the magnet creates a magnetic field. You have a moving charge in a magnetic field, and great, now you can actually have a Lorentz force. The Lorentz force deflects these particles because all the particles have different charges and different masses. Okay, remember that the equation for the Lorentz force includes Q, the amount of charge that the particle has, right? So the particles that have more charges are going to have more Lorentz force. If they have more Lorentz force, what's going to happen?
They're going to get deflected more.
They'll get deflected more. So out of these, which of these little detectors, which one of these ions has the most charge?
One on the left.
The one on the left, correct. Right, because it was deflected the most. Okay. Now there's also a mass effect too. This is something that doesn't have to do with electromagnetics, but it has to do with just basic particle, basic classical mechanics. A particle moving at a velocity has inertia, right? Inertia, like the more mass something it has, the harder it is to get it to change direction. And so the heavier atoms don't deflect as much, so they end up going here, and the lighter ones end up going this way. So there's two things that comes into play. One is the charge, and one is the mass of the particle. So in mass spectrometrists, they combine both into an M/Z ratio. So M on the top, and then the charge on the bottom. Okay. The heavy and less charged atoms will go into this side of the device and go into be detected by the detectors on this side, and the light and highly charged atoms will be deflected here and detected on this side. All right. Assuming that these are positively charged ions, can someone tell me which direction is the magnetic field oriented? So see if you can figure this out. Right-hand rule. Everyone think about this right-hand rule.
Where's the force?
The
force is...
Yeah, well, so which direction is the force? Yeah, which direction is the Lorentz force? We can start with that. So the particles are getting deflected over to they're getting deflected downwards, right?
Well, it changes everywhere because it's a curl.
Yeah, it does curve.
The B field will become
at a specific spot.
Well, let's do this. Here, let's start at this point, right at the entrance to the magnet. Okay?
At the entrance, it's facing down.
I'm sorry?
At the entrance, it's facing down.
So at the entrance, yeah, the particles are starting to deflect off this way, right? They're veering off to the right. Or in the way this thing is oriented, it's veering downwards, right? So the direction of the force, your thumb is going to point in the direction of the force. So thumb pointing down. What direction was the particle moving? Particle's moving from left to right. So first finger, index finger pointing from left to right, thumb pointed down. So the magnetic field must be
pointing out of the screen.
Yes, coming out of the screen, coming out of the page. Right. So the way that we would denote a magnetic field coming out of the page is like this. Oops. Oh. You draw a circle like this, and then you draw a small dot in the middle here. Okay, that means it's coming out of the page. Going into the page is a circle with a cross through it, like we saw in the previous slide. So this is really cool stuff. This is the stuff that physicists and chemists use to detect atoms and how big those atoms are and how much charge they have. All right, now let's get into the magnetic forces. All right, we talked about forces on individual moving charged particles. Now let's talk about forces on a segment of wire that's either straight or a segment of wire that's a loop. Okay, so there's two ways we can use the Lorentz force. All right, one is just on atoms that are moving on their own. That's mass spectrometry. So these are charged particles moving through a vacuum, essentially. The whole thing is in a vacuum. Excuse me. The whole thing's in a vacuum chamber. All right. But how we end up using these magnetic forces in the real world is something we use them in like electric motors, for example. All right, and in that case, the currents are normally moving through wires. Okay, so this slide is just about how there could be a force exerted on a wire if the wire has current flowing through it. All right, just a simple example here. So qualitatively, let's quickly look at this. All right, in this example, the magnetic field, notice that the magnetic field has crosses in there. The cross means it's into the page. So, all right, so if everyone wants to try their right-hand rule, your index finger. The first example here is where the magnetic field is 0. All right. This black line is a wire. There's a current going through the wire. Actually, in part A, the current is equal to 0. In part B, the current is the current is going up. All right. So you imagine your index finger pointed upwards, your middle finger pointing into the screen, into the page, and then your thumb is pointing in the direction of the force. So the force is going from right to left, and so that deflects the wire. If the current is moving in the opposite direction, it's moving from top to bottom, then the Lorentz force is oriented in the opposite direction. It's oriented from left to right. And the wire would get deflected in the opposite direction. All right, any questions about that? So this is just a deflection on a wire. Now we can actually calculate how much force we get. What we're doing here is we're looking at each section of the wire. If you imagine breaking up the wire into small chunks, little segments, all right, and each one of those segments will have a small amount of charge in it, and we can call that charge dq. So again, what we're doing here is we are breaking up, we're taking this wire here. I should draw it in the same orientation as the example, so we're not confused. So the wire is like this, and we have a current flowing through there. And what we're doing here is we are breaking up the wire into small chunks like this. All right? And we're going to calculate the magnetic force on each one of these chunks. So in this case, B was going into the page. All right. Now, if we look at each one of these chunks, each one of these chunks, we'll draw this, has a certain amount of charge in it. Okay, we call this dq, right? That's the amount of charge in there. The amount of charge is equal to rho VE times A times dl. Let's look at why that's the case. All right, there's a charge density in the wire, rho VE. Remember, rho V is a volumetric charge density. How do you go from volumetric charge density to total charge? Triple integral, right? You just multiply by the volume. So the total charge Q is going to be equal to rho VE times the volume. All right, so rho VE times, if this has some kind of cross-sectional area A, let's say it's a rod, like a square rod. So there's some kind of cross-sectional area A, and then there's also a length. And that length we're going to call dl. All right, so that's the total charge contained in that little box, that little segment of the wire. And rho VE is equal to, the charge density is equal to the number of charge carriers that you have in the material. So this is a material property, and then E is a constant 1.6 times 10 to the negative 19. So that's where these two numbers come from. So we did that to figure out the amount of charge in that little segment. The force on that segment, all right, we're only considering the force on that little segment. That's why we call it dF. F is the force on the entire wire. dF is just the force on that little segment. So dF is equal to Q times, Q is the amount of charge, that's what we just calculated, times U, the velocity, times B, the magnetic field. Okay, and so the Q is NEA times DL, and the the velocity is given by the U sub E, right? That's the velocity of an electron. So there's a lot of concepts here. At this point, this portion here actually is equal to the current. Why? Let's think about what the definition of current is. The current was charge density times the velocity at which the charges were moving. Okay? Think back to the last module when we talked about current, electrical current. The equation for electrical current was charge density times the speed at which they're moving. So basically this times this. So this whole section here becomes I, right? NE times E times A times U sub E is equal to the current. All right, and the DL just comes down here. So it's I times DL cross B. All right, so the total force, remember DF was just the force in that little segment. All right, so each one of these little segments is experiencing a magnetic force, and that magnetic force is equal to, we'll call this DF, I times DL cross B. If we want to get the total force on the entire wire, we have to integrate. We have to add up all the forces, add up the forces on all these little segments. Okay? And adding up all the forces means integrating. All right, so the equation for the force on one of the segments, this is one segment, is this. So the total force is just the integral of this. So force magnetic, the total force on the wire, Fm is equal to the integral of I dl cross B. All right, and that's the equation here. All right, so let's just circle that. So this is the total force on the wire. So you're going to have some homework problems not deriving this. You may have some homework problems where you use this equation. Calculate the magnetic force on a segment of wire, current carrying wire.
So how come the current deflects and then deflects back the other way?
So this is the example B is when the current is the direction of the current is going from down to up. And example C is when the current is going in the opposite direction. So if you do the right-hand rule in both cases, you'll see that in part B, the Lorentz force is going to be from right to left. In part C, since the current's going in the opposite direction, you'll see that the Lorentz force is actually pointing from left to right. So it deflects the wire in the opposite direction.
Is this with a negative charge? Positive charge.
These are all positive charges. Yeah. Remember when we define current is moving charge and moving positive charge.
Is the line integral along DL just equal to the total length?
If the field is, if this is uniform, if the magnetic field is uniform everywhere, then yeah, this equation then simplifies to just the length times B. It's a good question. So just to make sure that everyone got Noah's point there, so this is the total magnetic force on the wire. It involves this integral. But as you know, like with some integrals, if the fields are uniform, then the integrals simplify quite a bit. Right? You can just multiply by the length. That's the case here as well. If the magnetic field, if B is uniform everywhere in the wire, and the wire is just a straight line, then this integral just becomes the length of the wire times B.
times current. Yeah.
I'm sorry?
The current times length times cross between. Or is current not even?
Oh, well, I should say in this case, the current, the current is going from, let's take this one for example. The current is going from bottom to top, right? The magnetic field is going into the page, and so the Lorentz force is oriented from left to right. It's oriented from right to left. I'm sorry. It's going this way. All right. So if this integral dl cross b, dl basically isn't changing, right? Because dl is just, if we're integrating from the bottom to the top, the dl is just going to be z. It's going to be z hat times dz. The magnetic field isn't changing because the magnetic field is fixed. It's a uniform magnetic field. All right. So this integral would then become dz times z hat times b0 times x hat. All right, we can write that down. In the case, I just want to show everyone an example of this. In the case of b, this will be equal to I times the integral. Let's call this from z equals 0 to z equals h, the length of the wire. We can call this, or we'll call it L, the length of the wire. This would be z hat dz. That's what the dl vector is, crossed with the magnetic field is, we call that B0, that's the magnitude, and it's pointed in the x hat direction. So let's just go through and solve this real quick. So I times z equals 0 to L. So this cross product here is equal to the magnitude of this times the magnitude of this. So this is dz. Magnitude of the first term, the magnitude of the second term is b0. And then the third term is sine of theta. And that's the angle between these two. And so this is just the sine of 90. And this, of course, is equal to 1. So, so then it becomes the integral of dz from 0 to L times b0. This is a constant. This is also a constant. So this really simplifies into I times b0 times L. Okay, good. We have 15 minutes left, so we'll want to talk about torque and torque on magnetic on loops of wire. All right, let's first remind ourselves what torque is. Where we're going with this, by the way, is that what we're going to find is that if you have a loop of wire, we've been talking about what happens in just a segment of wire, one straight segment of wire. But if you have a loop of wire, something that looks like this, and you put that loop in a magnetic field, something interesting happens. You actually generate torque on that loop. So you can cause that loop to turn. Okay? This is important because this is the basis for electric motors. Electromagnetic motors. Okay. All right. So before we get into that, we have to do a quick review of torque. This is a concept from mechanical engineering, or you may have seen it from physics as well. Torque is a force that would cause an object, or mechanical engineers call it a body. It would cause an object or body to rotate about an axis. And the way it's defined is like this picture that you see here. Imagine that we have a wheel, and then we have a dowel rod, like some kind of rod stuck through it. So that defines the axis on which that wheel spins. All right, so we can define we can define this as the axis of rotation. Okay, so we're going to do another right-hand rule thing here. All right. This right-hand rule is it's not going to involve fingers. It's just going, well, it's only going to involve a thumb and your curled fingers, not your index and middle finger. So with this one, imagine your thumb is going to point in the direction of T. T is the torque vector, and T points, as you can see in this picture, T points along the axis of rotation. The axis of rotation is defined by the right-hand rule. Your thumb is pointing towards this axis of rotation, and your fingers, the fingers that curl around, that denotes the direction of rotation. All right? So in this example, you can see that the direction is counterclockwise, and your thumb is pointing in the z-hat direction. All right? So that's the right-hand rule there. The units for torque is given in newtons per meter, or newtons times meters. So for a given force, the longer the moment arm, the larger the force is. So let's talk about what the moment arm is. We're going to zoom in on this a little bit here. The definition of torque is D times F. D is the moment arm, and then F is the force. All right. Now, when we're calculating torque, let's put this in the context of a car, right? Imagine that's a wheel. Torque is the amount of rotational force that's being placed on that wheel. All right, so the acceleration of the car would obviously be dependent on how much torque you can put on that wheel. And by the way, you know, for you guys have seen these videos of electric cars like Teslas, like taking on the Lamborghinis and the Ferraris. If you haven't seen those videos, they're actually really cool videos to see.
As long as the race is short enough, the Tesla will win.
As long as the race is short enough, because electric motors actually put out lots of torque, much more than gas motors do, at zero velocity. Their torque actually starts to go down a little bit as you go to faster velocities. But at zero velocity, electric motors have tons of torque. So these things can just take off. Like it's crazy how fast the Tesla just released a semi-truck. I don't know if you guys heard about that, but they had this big event where they were showing that they have a new truck. And this truck can accelerate from 0 to 60 in like 5 seconds or something crazy like that. Can you imagine a truck on the highway going from 0 to 60 in 5 seconds? It's amazing. Like this is with a full load, by the way, with a full trailer behind it. It's insane.
The tires can stick to the road well enough for that.
Anyway, so torque. Getting back to our definition of torque. D, the vectors that we have here are D and F. D is the moment arm. It says vector in blue. All right, and you can see that the direction of D is going from the middle of the axis to the outside of the wheel. Okay, so the distance here, the magnitude is the diameter of the radius of the wheel, and the direction points from the interior of the wheel to the outside. Okay, this is called the moment arm. F is the force. So suppose that we are supplying some kind of force in this direction. So in this case, imagine that this is a wheel and we are manually applying a force at the end, at the surface of this wheel, and the resulting torque will be T, and that torque will be this vector T here. Okay. It can go the other way too. If you have an electric motor that's known to apply certain torque, and you have a certain diameter of wheel or radius of wheel, you can calculate the resulting orthogonal force here. Let's look at the directions here. Directions are very important. D is pointed from the interior of the axis of the wheel to the outside of the wheel. T is pointed in the direction of the axis of rotation, and then F is perpendicular to both of them. So F, you can see here, is the force here. It's orthogonal to D. All right, so that's the force that would be on the end of that wheel that's generated. All right, now one of the interesting things about torque is that the larger the wheel is, the more torque you get for an equal amount of force. So let's say we made the wheel twice the size, twice the radius, but we applied the same force to the end of the wheel. We get twice as much torque. Okay? Or if you think about it in the opposite sense, if your wheel is twice as big, like if you have a big truck wheel versus a small passenger car wheel, the truck wheel is going to require twice as much torque to get the same amount of force on the surface of the wheel. All right, so that's torque. Now, we're going to talk about magnetic torque in a current loop, and then how that can actually cause this thing to spin. All right, so imagine here that we have a loop here, and then the magnetic field is pointed from left to right. Okay, the loop, the current goes in a counterclockwise direction in this loop. Okay, so I want you guys to figure out just by looking at this. Now this loop, I want to keep in mind here that this is the y-axis and this is the x-axis. What is going to be the axis of rotation? I want you guys to see if you can figure that out.
What do you mean the axis of rotation?
If you put this loop inside the magnetic field, okay, the loop, what I'm telling you is that the current is going in the counterclockwise direction and the magnetic field is going from left to right. Which is the axis of rotation? What will be the axis of rotation of this current loop? What I'm telling you, I'm telling you that this current loop, this loop of wire will actually have a torque end up being applied to it. So which direction will this loop of wire rotate is what I'm asking. The way you can figure this out is think about the forces on each one of the segments of this wire. There's 4 segments of the wire. 1, 2, 3, and 4. For each one of those 4 segments, I would like you to apply the right-hand rule, apply the Lorentz force, the direction of the current, you know what the direction of the magnetic field is, and figure out what the resulting force on this segment of wire is going to be. Each one of these 4 segments is going to experience a different force. All right, and if we consider what all those 4 forces are, you can imagine which direction this thing might turn or rotate. All right, so take a minute and see if you can figure that out. Because once you figure that out, the rest of it is just math. Maybe we can start with segment 1.
It's going to have force coming out of the screen at us.
Out of the screen at us, right? Correct.
Right.
Right. So I want if everyone wants to follow along. First finger's pointing down. That's the direction of the current, because that's the direction U. It's U cross B. So U is going down, direction of the current. B is going from left to right, like this. Thumb points in the direction of the force. So the force on the first segment of wire is coming out of the page. How about segment 3?
It's going into the page.
It's going into the page. All right, now think about this. If you have a loop and one side is kind of coming out of the page, the other side is going into the page, you see how there's a torque being applied to that wire? How about segments 2 and 4? This is interesting. Why is it 0? Why is it
Sine 0 is 0.
Sine of 0 is 0, correct. Mathematically. Like what in 2 and 4, what you notice is it's U cross B, right? But U and B are in the case of 4, in the case of segment 4, U and B are pointed in the same direction. If you have 2 vectors pointed in the same direction and you take the cross product between them, the result is 0. Because of what Isaac just said, the sine of the angle between them is 0. So the cross product ends up being 0. The same is true if they're 180 degrees apart. In segment 2, the current is going in one direction, B is going in 180 degrees in the opposite direction.
You can't bend your fingers that far.
Yeah, exactly. So the forces on segments 2 and 4 are 0, but the forces on segments 1 and 3 are equal and opposite in magnitude. So one is going into the page, one is going out of the page, so that causes this rotation to happen. So the rest here is really just math. I just want to walk you through it real quick. You calculate the 4 forces, one on each segment of the wire. Notice that this shouldn't say F1 and F2, it should be F2 and F4. So let's fix that. All right, so F2 and F4 are 0. F1, the force is equal to I times the length times the magnetic field. Okay, remember in this previous example here, we found that the magnetic field is equal to I times the magnetic field times the length of the wire. Okay, if they are 90 degrees apart, or if they are orthogonal. So I times the length times B0. Okay, and we put in the directions here too. So the direction here is I times B naught. That's the magnetic field. This is in the z hat direction on segment 1. On segment 3, it's in the negative z hat direction, equal and opposite. So if you want to calculate the torque, you have to add up all of the components. There's some torque being added by segment 1. There's some torque being added by segment 3. So D1 crossed with F1 plus D3 crossed with F3. So D1 is the moment arm. As I mentioned, the magnitude of the moment arm, the magnitude of D1 is the distance from here to here. It's the distance between the axis of rotation to the edge of the loop. So this loop had a distance A, as you can see here. This is A. And so the distance from here, the origin, to segment 1 is A over 2. That's where this A over 2 comes from. The negative sign is because it's pointing in the negative direction, from right to left. To get from the origin to segment 1, you have to go in the negative x hat direction. So that's why that has a negative x hat associated with it. F1 is the magnetic force, which we just calculated up here. So IB times B0 in the z hat direction. The second term is x hat times A over 2. So that's the moment arm going from here to here. And the negative z hat times IB times B0. That's the force that we calculated in segment 3, F3. You add these two, you do this cross product, you add them up, and you get y hat times I times small a times small b. This is A, this is the dimension here, and this is B, dimension here. So it basically ends up being the cross-sectional area of the wire. I is the current, A is the area of the wire, area of the loop, and B0 is the magnetic field. So the torque scales with the amount of current and the size of the loop. This is why if you need to generate a lot of torque, you need to have a big loop. All right. Now, really quickly, if you just want to spend like a few minutes, we can go over this as well and just finish off magnetic torques. I just want to go through this other derivation, a more generalized one. Okay, this will only take like 5 minutes or so. This was an example is when the magnetic field is in the same direction in the plane of the loop. And this one is just a more general example where the loop is actually rotating. So as the loop rotates, the magnetic field is no longer in the plane of the loop. Okay, so this might be what it looked like initially before this wire loop started rotating. But once it starts rotating, then it's a more generalized situation like this. So it's worth it for us to look at that really quickly. So the important parts here, you still have segments 1 and 3. Those are the ones generating the torque. F2 and F4, they still don't generate torque, okay? So F2 and F4 exert no torque for the same reasons as before. F1 and F3, same thing as before. We already calculated what the force is. So force 1 and force 3, not changed. Same calculation, nothing's changed there. In fact, the result is still the same. The difference here is the torque. Okay. In our definition of torque, this force here, all right, T is equal to D cross F. What's happening is as the magnetic loop is rotating, the F is not changing, okay? We calculated the F. The F is in the Z hat direction, right? So the direction of F is not changing, but what's changing is D because the thing is rotating, right? The loop is rotating, so the moment arm is rotating, so D is changing its angle, but F is still in just the Z hat direction. So the direction here is fixed, but the direction of D is changing. So what's going to happen to the torque? Let's see if we can just think about this qualitatively. What happens if D and F are perpendicular to each other? You get the maximum torque. What happens if D and F are parallel to each other?
Zero.
You get zero torque, right? So what ends up happening, the direction of the force is still the same. It's still in the Z hat and negative Z hat direction. But the moment arm direction is changing. All right? So when the moment arm direction and the force are parallel to each other, the torque is going to be zero at that point. When the torque is zero, then the thing stops rotating, right? So that's where this sine term comes from, okay? So I just want you all to know that this derivation is exactly the same as the previous slide. The only change in the torque now is the sine term, okay? Sine of theta is the angle what the loop is at currently. And as you'll see that when the loop turns 90, when the angle is equal to when it's equal to 0 degrees or 90 or 180 degrees, the angle and the force is going to end up being 0. All right. So when that force becomes 0, the magnet or the motor stops turning. It just turned a half a turn. So how do we keep the magnet? How do we keep that motor turning?
Well, you reverse the direction.
You reverse the direction. Have any of you worked with motors before? You seen motors before? Okay. I just want to. I'll end with this, just so you can see how DC motor. Let's see if we can find a quick animation of it. There we go.
Of the current, so the force is always on each loop, side of the loop. The force would always point the exact same way. So as it turns over, it's going to stop and oscillate back and forth.
Okay.
So to keep it spinning in the same direction, when it reaches the top, you have to reverse the current direction.
Yeah, check out this animation. This is pretty cool. The animation is showing that the current changes direction. So how do you change the direction of the current? You can't rewire the thing, right? So one of the ingenuities of a motor is actually in how this little loop is designed. You see how this rotation, this cylinder has two contacts on it? Like one covers half the cylinder, the other one covers the other half of the cylinder. So as this thing turns, you see how the positive end is connected to one of the contacts, and then as it turns 180 degrees, now the positive terminal is connected to the other contact?
Yeah.
That's what reverses the direction of the current. It's something like a brush motor, right? So anyway, I think that's a pretty neat. This is another quick look at it. This side is you have two contacts here. As the thing turns, once it turns 180 degrees, the current reverses direction, and now you apply torque. Now you keep on applying that torque so the motor can keep spinning. All right. So that's your primer on magnetic forces, magnetic torques, and that's the basis of electromagnetic motors. It's all like magnetostatics.
Of course, the velocity is going to pulse because
You will get some pulsation in the rotation.
that's why they don't have two-node motors.
Right.
Like for everything,
Right.
six or
Multiple motors is where it's at right now.
12, however many they think they can synchronize.
Mm-hmm. Mm-hmm.
So I did have a question earlier, I didn't want to interrupt class for it, since it's not
Oh yeah.
a direct